Our final presenter this evening is Dr. Ken Golden, a distinguished professor of mathematics and adjunct professor of biomedical engineering. He will take us on a journey of seemingly unrelated areas of science, including engineering, Antarctica, and possibly even challenging your perceptions about where math can take us. Pay attention, because there might be a test at the end.
Thank you, Mitzi. You may all be wondering, what in the world does sea ice in Antarctica, a semiconductor in your laptop, and Harry Potter's invisibility cloak have to do with each other? As it turns out, they're all studied by a group of professors in the mathematics department, of all places, at the University of Utah. For example, Graham Milton was the first scientist in the world to be able to prove rigorously, mathematically, that you can actually cloak objects and make them appear to be invisible. In related work, Fernando Guevara Vasquez is developing metamaterials like this to thermally cloak objects. And at the heart of all this are these complex materials called metamaterials, which have complex structure that exhibit properties that are not normally found in nature. Now, for the past half century, I've been studying a multi-scale composite material called sea ice. Now, as you freeze seawater, you can't incorporate the salt into the crystalline structure. And so you get these tiny microscopic brine inclusions whose volume fraction, geometry, and connectivity depend critically on temperature. Moving up in scale, as snow melts on the top of Arctic sea ice, it forms these beautiful iconic blue melt ponds that ultimately determine how much solar radiation is absorbed by the ice pack or reflected back into space. And then moving up into scale on the ice pack itself is also a composite material consisting of ice flows in a seawater host. Now, on one of my first expeditions to Antarctica, as the ship parked, it broke the ice. And one of the data that we were very interested in was seeing how rapidly the ice would form in that what's called a lead. And now we knew this ice was very thin. You could see this gray patch there. That's what we were looking at. And we knew it was very thin, but also it's not lake ice. It's laced with fluid inclusions. And so my great idea was to have my colleagues hold my legs as I laid out on the ice and hopefully did the measurement. And what could possibly go wrong? As it turned out, we were in a big storm, and the ice was moving at 1 meter per second relative to the water, and the water itself was -2 Celsius. So if you go in, that's pretty much the end. Nevertheless, I was able to do the measurement, spread my weight out, and we measured that it was 7 centimeters. And at that point, we thought, maybe this is not the best idea. Maybe we should think up something different the next time. Now, on that same night, which was Utah's Pioneer Day of 1994, to the right of that spotlight, I saw something extraordinary. I saw this seawater percolating up and flooding the surface of the sea ice. And I realized that what I was witnessing was the formation of a connected fluid pathway from the bottom to the top that allowed the seawater to percolate up and flood the surface. And that brought us into thinking how to analyze this into what's called percolation theory, which is the mathematical theory of connectedness. This is the classical two-dimensional square lattice percolation model. On the left, about a third of those edges or bonds are filled, but there's no connected pathway. On the right, you see about 2/3 of these bonds are present, and there's a connected pathway. But one of the critical questions is, what's the smallest proportion of the bonds that need to be there in order to be able to have the existence of one of these connected pathways? And this is called the percolation threshold. And it turns out that this is very similar to the critical point, say the critical temperature of water, where at 0 degrees C it freezes, and at 100 degrees C it turns into vapor. And unfortunately, though, for this classical two-dimensional model, the percolation threshold is exactly 50%. And this is about 10 times what we expect for sea ice. And so we turned to our background in mathematical materials science to realize that the microstructure of sea ice, shown in the upper left, is very, very similar to the microstructure of compressed powders, which were used in the development of stealthy coatings to cloak aircraft from radar. And we used the percolation theory developed for these compressed powders to figure out what the percolation threshold for sea ice and out pop the 5% that we were very interested in. And so this is the first example of what I like to call cross-pollination, where we take ideas and methods from seemingly unrelated areas of science and engineering and bring that to bear on sea ice, and vice versa, where we take some of the mathematics that we've developed for sea ice to solve problems in seemingly unrelated areas of science and engineering. So I'd like to give you a few more examples of this. One, as you can see here, is this close relationship between the porous microstructure of sea ice and the porous microstructure of human bone. Now, you might have noticed that I had a little trouble walking out here, and I'm standing at a podium rather than walking around. 5 weeks ago, literally to the day, I totally busted my hip up at Solitude. So I've had my own personal experience with the porous microstructure of human bone. And so with one of our mathematical materials scientists, Lena Cherkayev, we use the mathematics that we developed for understanding the propagation of electromagnetic waves through sea ice to develop a totally new method of monitoring the onset and progress of osteoporosis, as you see in these lower two slides. Now, another example is another very important aspect of our research is studying the interaction of ocean waves as they propagate through the sea ice pack. This turns out to be important, trying to understand the freezing of the ice pack in the fall and then the decay of the ice pack in the summertime. And what's interesting here is that we use the mathematics and physics of semiconductors to help guide us and help our analysis and the questions that we ask in trying to understand the propagation of waves through the sea ice pack. And then the last example that I want to tell you about is based on what's called twisted bilayer graphene. So you may have heard of graphene. This is a single layer of carbon atoms that won the Nobel Prize for its discovery. It's 200 times stronger than steel and 1/6 the weight. But if you take one layer of graphene and another layer of graphene and twist them slightly relative to each other, you get something that has extremely interesting electronic properties. And if you get the angle just right, the so-called magic angle, you actually get a superconducting material. And so what we did was take the mathematics that was motivated by semiconductor physics as we applied to sea ice, and we take two purely mathematical lattices and twist them relative to each other, and that provides a template where we can arrange two different materials and make a totally new class of metamaterials that we call twisted bilayer composites. However, it's not just on the atomic scale, but on any scale, and also for many different properties, not just electronic properties. And then one of the things that really distinguishes our research program, particularly among other math departments, is that we actually take students, mathematics students, science and engineering students, to the polar regions to immerse them in experiments and get their hands dirty on these types of things. And I need to say, though, that we've been doing this for a long time, and we have an amazing track record. We've always brought back over 85% of the students that we take down there. and so this past May, Jody Reimer, who was a postdoc of mine, and now she's an assistant professor in both mathematics and biological sciences, we led what we called a mathpedition to the Arctic. And we brought 7 math students from high school up to Ph.D., all doing theoretical research on sea ice modeling. And and we basically immersed them in experiments on the physics and biology of sea ice. And one of the cool things that Jody has brought is a lot of cool toys and instruments and so on, so we can study the microbes that live inside these tiny millimeter scale brine inclusions. And so in the lower right, you see what's called a nematode, the most numerous animals on Earth. And on the left, you see algae. And in the middle there, you see a polar bear. And what happened was, on our first morning there, we were on our way to the grocery store, and we ran into this very agitated, very hungry polar bear. And fortunately, we stayed in our vehicles because that polar bear could have closed the distance in about 5 or 6 seconds. So finally, you might be wondering, like, why in the world are these math professors going to the farthest reaches of the earth to do all these studies about materials and related types of problems? And to let you know, I'm going to recount an interesting experience I had on my first trip to Antarctica with the Australians aboard this beautiful icebreaker, the Aurora Australis. And so we went out to do some experiments at about midnight, and then we came back in and went to sleep. And then at 2:30 in the morning, the fire alarm's going off. And I'm saying, like, why are they having a fire drill now? And so we all were supposed to muster at the fantail of the ship where the helicopters take off and land. And the next thing I heard was, please don't be alarmed, but we have an uncontrolled fire in the engine room. 10 minutes later, please don't be alarmed, but we're lowering the lifeboats. And I'm thinking, I prove theorems for a living. What in the world am I doing on a burning ship in Antarctica? And so, but now with some hindsight, and also thinking about using mathematics to study things like invisibility cloaks, I think what this interesting and unique group of math professors is doing is taking mathematics to places it's never been before. So thanks very much for listening, and have a good evening.